How does the tech that runs our world really work? We break it down to its fundamental truths. This is First Principles.
You're scrolling through your feed late at night when you see it. It's a video, probably shot on a phone in a warehouse or a lab, and it shows something that even now feels impossible. A machine made of metal and plastic and wires is walking, not shuffling, not rolling on wheels, but walking, bipedal, upright, with a smooth, confident gait. It steps over a cable on the floor, adjusts its balance, and then it does something else. It reaches out with a five-fingered hand, picks up a box, and places it on a shelf. It turns, sees another person, and hands them a tool. There's no movie magic here. This is real. You've seen these videos from companies like Boston Dynamics, Tesla, Figure AI, and you feel a strange mix of emotions. There's awe, certainly. Awe at the sheer engineering brilliance. But there's also a little bit of unease, that little shiver of the uncanny. It moves in a way that is so fundamentally biological, so human. We take it for granted that our technology will get better, faster, smarter. But this feels different. This is a leap. We are used to robots as giant, menacing arms on an assembly line, sealed off in cages for safety. We are used to robots as cute little vacuums bumping into our furniture. But a robot that can walk into your kitchen, open your refrigerator, and get you a drink, that's something else entirely. It feels like a machine has broken a rule, like it has learned a secret that was supposed to be ours alone. And in that moment of wonder, you might have a fleeting thought. You might think it's all about a powerful computer, an incredibly smart AI that's thinking about how to walk. Or maybe it's about having incredibly strong and precise motors for legs. And those things are part of it, of course. But have you ever stopped to wonder how that actually works? What are the fundamental rules, the first principles, that allow a pile of inanimate matter to achieve the living grace of a bipedal stride? What does a robot have to know about the world to take a single step without falling on its face? Today, we are opening up one of the most complex and fascinating black boxes of our time, the humanoid robot. We're going to look past the whirring motors and the lines of code to find the surprisingly simple, elegant, and ancient principles that make it possible. And what we'll discover is that the secret to building the robot of the future has less to do with inventing something new, and everything to do with copying something very, very old. The magic of the modern humanoid robot is its growing generality. For decades, the word robot meant a specialist, a machine designed to do one thing perfectly a million times. Think of the automotive assembly line. A robotic arm, bolted to the floor, picks up a car door, moves it exactly 27.5 inches, rotates it 42 degrees, and holds it perfectly still while another arm welds it. It can do this for 20 years without a coffee break. It is faster, stronger, and more precise than any human. But ask that same robot to pick up a screwdriver that someone dropped, and it's completely useless. Its world is a cage. Its reality is a set of pre-programmed coordinates. It doesn't see a car door. It sees a destination in three-dimensional space. The world outside that cage, the messy, unpredictable human world, is completely alien to it. The new wave of humanoid robots is the exact opposite. You see them in demonstration videos sorting packages in a warehouse, a task that involves identifying objects of different shapes and sizes. You see them making coffee, a process that requires delicate manipulation of a cup, a machine, and a dispenser. You see one from a company called Figure AI having a conversation with a human, identifying an apple on the table and then handing it to them, all while explaining its reasoning process. The magic isn't just that it can do these things. It's that the same robot can do all of these things. It's a generalist. The goal isn't to build a perfect coffee-making robot or a perfect box-stacking robot. The goal is to build a robot that can figure out how to do any task a human can do, just by watching us or by being told what to do in plain language. This is a profound shift. We are witnessing the transition of robotics from pure, rigid automation into the realm of artificial intelligence. These machines aren't just running a program. They are perceiving their environment, making decisions, and learning from experience. They seem to be breaking free of the cage, ready to walk into our world and work alongside us. The promise is enormous. A future where robots can care for the elderly, respond to disasters in places too dangerous for people, or simply take on the dull, dirty, and dangerous jobs that we would rather not do. It feels like we are on the cusp of that future, the one we've seen in science fiction for 100 years. But this leap forward, this sudden explosion of capability, makes the central question even more urgent. How did we get here? How did we solve the single hardest problem that held robotics back for more than half a century, the problem of just standing up? Before we can understand the robot, we have to understand the problem it's trying to solve. And the problem is gravity. More specifically, it's the profound, almost comical difficulty of bipedalism, of walking on two legs. The dream of a mechanical person is ancient. You can find it in the Greek myths of Hephaestus, who forged mechanical servants, or the myth of Talos, the giant bronze automaton who guarded the island of Crete. The desire to build an artificial copy of ourselves is woven deep into our history, but for centuries it was pure fantasy. The first real attempts began in the 20th century. In the 1970s, at Waseda University in Japan, a team led by Professor Ichiro Kato built what is widely considered the first full-scale humanoid robot, WABOT-1. It was a remarkable achievement for its time. It could walk, albeit very slowly and carefully on a flat floor. It had vision systems that let it measure distances to objects, and it had hands that could grip. But watching videos of WABOT-1 is a lesson in just how hard this problem is. It moved with a stiff, shuffling gait, taking tiny, pre-planned steps. It was a puppet, executing a precise choreography. If the floor was even slightly uneven, or if you gave it a gentle nudge, it would have toppled over instantly. It was a machine pretending to walk. The core challenge wasn't about making the legs strong enough or the computer fast enough. The challenge was, and still is, balance. Think about how unstable the human form is. We are an inverted pendulum. A heavy torso and head perched precariously on top of two long, spindly legs, with a tiny contact patch on the floor. The soles of our feet, most of our time spent walking is technically a state of falling. Our natural state is not one of stability, like a four-legged table, but one of constant, dynamic instability. For decades, engineers tried to solve this problem with pure control theory. They treated the robot like a math problem. If we can calculate the exact center of gravity, and the exact forces from the motors, and the exact friction of the floor, we can create a perfect model and tell the robot exactly how to move its joints to stay upright. This is called the Zero Moment Point Method, or ZMP. It's the idea of keeping the center of pressure, the point where all the forces meet the ground, squarely within the footprint of the robot's feet. This approach worked, sort of. It produced robots like Honda's famous Esimo, which debuted in the year 2000. Esimo was a revelation. It could walk smoothly, it could climb stairs, it could even run in a slow jogging motion. It was a marvel of pre-programmed precision. But Esimo, for all its grace, was still fragile. It was operating on a perfect internal map of its own physics, and a perfect understanding of its environment. It excelled on flat floors and carefully designed staircases, but take it outside onto a grassy lawn or a rocky path, and the math falls apart. The real world is messy. The ground isn't perfectly flat, and a foot can slip. A gust of wind can push you. In the real world, a pre-programmed dance is not enough. You need to be able to react. You need to be able to improvise. You need to learn how to fall and how to catch yourself. The pioneers had defined the problem perfectly. They had proven that building a walking robot was a monumental challenge of physics and control. But they also revealed the limits of a purely top-down programmed approach. To truly conquer bipedalism, the robot couldn't just be given the sheet music. It had to learn how to play jazz. The revolution that we are seeing today came from a completely different philosophy, a new way of thinking about the problem. It came from deciding to stop fighting instability and start embracing it. So, how do you build a machine that can stand, walk, and navigate our messy world? We have to open the box, and the first thing we find inside isn't a super powerful computer or a futuristic power source. The first principle of a modern humanoid robot is a new perspective on what walking even is. Let's use an analogy. Imagine you are trying to balance a long broomstick vertically on the palm of your hand. What do? The one thing you don't do is hold your hand perfectly still. If you did, the broom would instantly fall over. Instead, you are in constant motion. You watch the top of the broomstick, and as it starts to lean, you quickly move your hand underneath it to catch it. Your hand is always moving, making tiny, rapid adjustments. You are not maintaining a state of perfect, static balance. You are managing a state of continuous, controlled falling. This is the first principle. Human walking is not about being stable. It is the art of the controlled fall. When you take a step, you lean forward, shifting your center of gravity ahead of your feet. For a brief moment, you are falling. Then, you swing one leg forward and plant it on the ground, catching yourself just before you topple. Then you repeat the process. It's fall, catch, fall, catch. We are so good at it, we do it without thinking. It's the most natural thing in the world. For a long time, roboticists tried to prevent the robot from falling. The new approach, pioneered by companies like Boston Dynamics, was to accept that falling is inevitable. In fact, it's essential. They started designing robots that use this dynamic stability. Just like you balancing the broomstick, the robot is constantly gathering data about its own state, its tilt, its velocity, its joint positions, and using that data to predict where it needs to place its next footstep to catch itself. This is why you can see videos of engineers pushing these robots. The robot stumbles, windmills its arms, takes a few rapid corrective steps, and stays upright. It's not running a pre-programmed "I've been pushed" routine. It's dynamically recalculating in real time. I am falling in this direction, so I must place my foot over there to stop the fall. It's managing instability. But how does it know it's falling? This brings us to the first piece of hardware, the first irreducible component. Buried deep in the torso of every humanoid robot is a tiny, crucial device called an inertial measurement unit, or IMU. It's the robot's inner ear. It's the hardware that gives it a sense of balance. You have one in your pocket right now. It's inside your smartphone. It's what tells the screen to rotate when you turn your phone sideways. An IMU is actually two different kinds of sensors working together. The first is a set of accelerometers. As the name suggests, they measure acceleration. A robot standing perfectly still will have one accelerometer pointing down that reads an acceleration of 9.8 meters per second squared, or 1 gram. That's the pull of gravity. If the robot starts to fall forward, the accelerometer that points forward will detect a change. It feels the motion. The second part of the IMU is a set of gyroscopes. A gyroscope is a device that is very good at resisting changes to its orientation. By measuring the force it takes to move the gyroscope, the sensor can calculate exactly how fast the robot is tilting, rolling, or yawing. This tiny chip provides a constant, high-speed stream of data. I am tilting forward at 5 degrees per second. I am accelerating sideways at 0.2 grams. This is the raw data of balance. It's the robot's vestibular system. It's the fundamental input that tells the robot's brain, the broomstick is starting to lean. Without this constant awareness of its own orientation in space relative to gravity, the robot would be helpless. It would be like trying to walk with your eyes closed during a massive earthquake. So, the IMU tells the robot it's falling. Now what? It has to move its legs to catch itself. This is the job of the actuators. These are the muscles of the robot. In some early models, like the famous Atlas robot from Boston Dynamics, these were hydraulic. They used high-pressure fluid to move pistons, giving them immense strength. It's why they had that characteristic loud whining sound. Hydraulics are incredibly powerful, allowing the robot to jump and do backflips, but they are also complex, messy, and energy-intensive. More and more, modern humanoids are moving to electric actuators. These are essentially very sophisticated, high-torque electric motors at every joint. The hips, the knees, the ankles. They are quieter, cleaner, and more efficient. But whether hydraulic or electric, these actuators have to be paired with another kind of sensor. They need to provide feedback. The robot's brain doesn't just send a command like, move the knee. It needs to know with microscopic precision the exact angle of that knee joint at every millisecond. This is called proprioception, the sense of self-movement and body position. The robot builds a complete picture of itself thousands of times a second. The IMU says, we are tilting forward. The joint sensors say, the left knee is at 45 degrees, the right hip is at 20 degrees. All of this data feeds into the robot's brain, its central computer, and this is where the real revolution has happened. This is where we move from pure mechanics to true artificial intelligence. In the old model, with a robot like a Simo, a team of brilliant engineers would have spent years writing the code that translated that sensor data into motor commands. The code would be a massive list of rules. If the forward tilt is greater than 5 degrees and the left foot is on the ground, then send X amount of power to the right hip motor. This approach is incredibly brittle. If you encounter a situation the engineers didn't think of, the robot fails. The new approach is entirely different. Instead of being programmed, the robot learns. This is done using a type of machine learning called reinforcement learning, and it works a lot like training a dog. You give the AI a goal, and you give it a way to receive rewards or punishments. Imagine you want to teach an AI to walk in a computer simulation. The AI, which we call the agent, starts out with no idea what to do. It can control all the virtual joints of the robot, but its initial movements are completely random. It flails around and immediately falls over. When it falls, it gets a negative reward, a punishment, like a little electric shock, but maybe just by pure chance. One of its random flails moves the robot forward a tiny bit before it falls. For that tiny bit of forward progress, it gets a small positive reward, a little treat. Now, you run this simulation not once, but millions or even billions of times. The AI's job is to maximize its total reward. Over millions of trials, it starts to connect certain actions with certain outcomes. It learns that flailing its arms wildly usually leads to falling, punishment, but that a particular sequence of moving its hips and knees leads to forward motion, reward. It is, through pure trial and error on a massive scale, discovering the physics of walking for itself. It learns a policy, which is just a fancy word for a strategy. This policy isn't a rigid set of instructions. It's a complex mathematical function that takes all the sensor data as input, the tilt, the joint angles, the velocity, and outputs the optimal motor commands to achieve the goal of moving forward without falling. Once this policy is trained in the simulation, a process that can take days or weeks on powerful computers, it is then loaded onto the physical robot. And this is the magical part. Because the AI didn't learn a specific dance routine, it learned the underlying principles of balance. When the real robot encounters a slightly uneven floor, its sensors pick up a tilt that is slightly different from what it experienced in the simulation. But because its learned policy is so robust, it can still calculate the correct corrective action. When an engineer shoves it, the IMU screams that it's experiencing a massive, unexpected acceleration. The AI's policy takes that input and instantly computes a series of stabilizing foot and arm movements. It hasn't been programmed how to react to a push. It has learned the general skill of maintaining balance in the face of disturbance. This brings us to a common misconception about these machines. When we see a robot perform a complex task, especially when it seems to be learning, our human instinct is to anthropomorphize. We imagine a thinking, conscious mind inside the machine, deliberating about its next move. We think, it sees the box, it understands that I want it, and it decides to pick it up, but that's not what's happening. The AI running on that robot is a cascade of highly specialized neural networks. One network, its computer vision system, has been trained on millions of images. It doesn't see a box in the way you or I do. Its job is to take a grid of pixels from a camera and, through pattern recognition, draw a bounding box around a cluster of pixels that it classifies with 98% confidence as box-like object. Another network takes that location data and combines it with the proprioceptive data from the arm, and its policy, trained through reinforcement learning, outputs the series of motor torques required to move the hand to that location. It is not thinking, it is calculating. It is executing an incredibly sophisticated, learned reflex. It is a masterpiece of optimization, of statistical correlation, but it doesn't have understanding or intent. The intelligence we see is an emergent property of these layered systems, all working together to achieve a goal set by a human programmer. Correcting this misconception is crucial. These robots are not our peers. They are tools. They are arguably the most advanced and impressive tools ever created, but they are tools nonetheless. They are a reflection of our own ingenuity, not the dawn of a new form of consciousness. We've now seen how the robot stands and how it learns to move. We've looked at the IMU that lets it feel gravity, the actuators that move its limbs, and the reinforcement learning that gives it the skill of balance. It seems like we have a complete picture. But we've missed the single most important principle. We've missed the unseen giant in the room, the one thing that makes this entire endeavor possible, and that explains the most fundamental question of all: why build them to look like us? Why a humanoid? Why go through all the immense trouble of solving the bipedalism problem? It seems so inefficient. If you just want a robot to move things around a warehouse, surely a machine with 4 legs or wheels or even a track like a tank would be more stable and easier to build. For decades, that was the prevailing wisdom. The most successful commercial robots, like the ones that move shelves in Amazon fulfillment centers, are flat-wheeled platforms. They are supremely efficient, but they operate in a world designed for them. A world with perfectly flat, polished concrete floors, wide corridors, and special barcodes for navigation. The moment you want a robot to leave that sanitized environment and enter our world, the human world, everything changes. And that is where we find the final, most profound first principle of humanoid robotics. The reason to build a robot in the shape of a human is not because it is an elegant engineering solution. It is because we have already spent 10,000 years of civilization making the world perfectly suited for that exact shape. Think about the room you are in right now. Look at the door. The doorknob is at a specific height, designed to be comfortably grasped by a human hand and turned by a human wrist. The door itself is a certain height and width to allow a human body to pass through. Now look at the stairs. Each step has a specific rise and run, a dimension optimized for the stride of a human leg. Look at the tools on a workbench, a hammer, a screwdriver, a power drill. Their grips are molded to the human hand. The interface on your stove, the steering wheel in your car, the keyboard you type on, the chair you sit in. Everything. Our entire built environment, our entire infrastructure, is a grand operating system designed for a single type of user, a bipedal primate, about 5 to 6 feet tall, with 2 arms and 2 5-fingered, opposable thumbed hands. This is the unseen giant. The most important design feature of a humanoid robot is not inside the robot at all. It is the world around it. By building a robot that conforms to the human body plan, we give it a universal key, a key that unlocks our entire world without requiring us to change a single thing. A wheeled robot can't climb stairs. A robot with a specialized gripper can't open a door. A non-humanoid robot would require us to rebuild the world for it, to install ramps, to create special interfaces, to redesign all of our tools. A humanoid robot, if we can perfect it, requires none of that. It can walk up the same stairs you do. It can open the same door. It can pick up the same hammer and hit the same nail. It can sit in the driver's seat of a car and drive it. This is the entire premise of Tesla's Optimus robot. To create a general-purpose worker that can slot into any factory or warehouse position that was originally designed for a human with zero modification to the environment. This principle changes everything. It reframes the central challenge. The difficulty of making a robot walk on 2 legs is not a bug. It is a feature. It is the price of admission. It is the immense upfront engineering investment that you pay to gain access to a world that is already perfectly configured for you. The humanoid form is not about nostalgia or science fiction fancy. It is a decision based on the cold, hard logic of ergonomics and infrastructure. It is the ultimate shortcut. We are not just building a machine. We are building a machine that is backwards compatible with civilization. So where does this leave us? We began this journey looking at a video of a walking machine, something that felt like magic. We saw a seamless, graceful motion and probably assumed it was the product of some impossibly complex, monolithic AI, a brain in a box that had figured it all out. But as we peeled back the layers, we found something quite different. We didn't find a single, magical solution. We found a stack of elegant, interlocking principles. We found that the foundation of it all isn't stability, but the mastery of instability, the art of the controlled fall, a lesson learned not from computers, but from watching a toddler learn to walk. We found that this physical dance is guided by simple, robust hardware. The inner ear of the robot, its IMU, constantly whispering to it about its relationship with gravity, and the muscles, the actuators, that translate digital commands into physical motion. And we found that the intelligence tying it all together is not one of programmed, rigid logic, but one of learning, an AI that builds its own understanding of physics through millions of simulated failures, developing a deep intuitive sense of balance that is flexible and adaptive, much like our own. But the final and most important principle was the one that was hiding in plain sight: the realization that the humanoid form is not an arbitrary choice, but a deeply pragmatic one. It is an acknowledgement that the most complex and valuable system is not the robot itself, but the human-centric world it is designed to inhabit. Building a robot that looks and moves like us is not an act of hubris. It is an act of humility. It is an admission that our world, with all its beautiful, messy, and ergonomic peculiarities, is the ultimate design constraint. Understanding the first principles of a humanoid robot does more than just demystify a piece of technology. It forces us to see our own world in a new light. It makes us appreciate the profound genius of our own bodies, which solve the problem of bipedal walking so effortlessly that we forget it is a problem at all. And it reveals our built environment for what it is: a legacy, a physical manifestation of our own form, a silent partner in everything we do. These new machines are not inventing a new way to exist. They are simply, after a long and difficult journey, learning to speak our native physical language.
You've been listening to First Principles. Until next time, stay curious.